Hello everyone, my name is Gerardo, and I'm here to talk about Cascade High Productivity Language, otherwise known as Chapel. So to start off, let's talk about the origins and history. So Chapel was developed by Cray Incorporated, which is now a part of Hewlett-Packard Enterprise after it got acquired. The origins of Chapel trace back to a project sponsored by DARPA, which is the Defense Advanced Research Projects Agency. DARPA is a U.S. government agency responsible for developing emerging technologies for national defense. They're known for initiating transformational projects like ARPANET, which led to the internet. In the early 2000s, DARPA launched the High Productivity Computing Systems Program. The HPCS program's goal was to dramatically increase the productivity of programmers working on supercomputers, aiming to create systems that would deliver high performance without requiring the very low-level, error-prone programming typically needed at the time. Cray's answer to this challenge was Chapel, designed to make writing code for massive machines faster, easier, and less burdensome. Chapel was first publicly released in 2009 and was a key component of Cray's Cascade supercomputer project. So now moving on to goals and philosophy. So Chapel aims to greatly improve programming's productivity for parallel applications, which is the reason why I was a part of the program. The language separates high-level algorithm design from low-level systems details like memory layout. It's designed to bridge traditional high performance computing programming, think C, Fortran, or MPI, with modern user-friendly languages like Python. Its key principles, general parallelism, control over data, placement, object-oriented, engineering programming support, they can be divided into two things, one being more focused on making sure it's optimal in terms of parallel programming and it's efficient, while the other part is focusing on how efficiently programmers can interact with it and how human readable it is and easy to program. So Chapel follows a multi-resolution philosophy. So this means that it hides complexity until you need to optimize for performance, allowing for rapid prototyping. So moving on to key features of Chapel. So Chapel supports multiple models of parallelism, data, task, and nested parallelism, all built into the language. It provides high-level constructs such as powerful arrays, slices, and parallel iterations for readable parallel code. It's designed for portability and scalability, which means that it can run from laptops to supercomputers, even targeting GPUs and clusters. The goal behind this is so you can code it all in one machine and then easily transfer it to a different one, and it should run exactly the same. Unlike languages that build on parallelism with libraries, Chapel offers a unified experience with native support. This approach reduces complexity and makes it easier to write, maintain, and scale parallel programs. So now moving on to syntax, here we have two different ways that we can parallelize for loops. So here is a for all, which creates a set amount of threads, usually based on available cores, which then gets distributed the amount of iterations. Meant for smaller similar tasks between iterations, load balancing happens when the thread finishes early. So here what's going to happen is that it's going to take the number of cores that are in your machine, then create that amount of task and distribute the amount of iterations, which in this case is 1,000,000 iterations, to those tasks that got created. Each task is then going to execute some set amount of iterations in parallel with the other task. In this case, there is a note that this is a race condition because they're all interacting with the sum. So now another instance of a way that you can loop through this is a code for all. So this creates a thread per iteration, and each thread owns an iteration. There's no load balancing, and it's meant for bigger independent iterations. Here, if you look to the code to the right, you'll see that we are creating a variable called numTask, which is based on the amount of cores in our machine. So what this is going to do is that the code for all, the thread ID in this case is just TID, in 1 to number of tasks. So here what's going to happen is that each task is going to get this line. And in our case, let's say we have 8 cores. So each core is going to get this instance of this. It's going to be like write line, hello world from task, like thread ID of numTask, right? So if there's 8 cores, which means that we're having 8 tasks be created, there's going to be 8 print statements saying like hello world from task 1 of 8. And because all of these are running in parallel with a core taking up iteration, there is no surefire way of knowing how these are going to print. So you could start with thread 1 printing first and then thread, let's say like 5. So there is no sequential way that we expect the print statements to happen because all of this is running in parallel. Another thing to note is that if let's say here we have like num task be greater than like the number of cores, what ends up happening is that Chapel will then create a queue, same thing as like usually happens where there's like just some created amount of tasks, and then the course just pick them up as they become free. Another thing to look at is the begin and co-begin. So the begin creates a thread where the code within the begin will be executed. So what happens here is that when you run this begin, a thread or a task gets created that is given this like line of code, and this is going to happen within all of these lines. So this is like similar as like before, you can't really predict the way that this is going to print. So these are 4 different threads that are then given each its own like independent task. So what's going to happen is that we're going to have all of these 4 things print, but the order same thing cannot be predicted. Now looking at the co-begin, so the difference between the co-begin and the begin is that the co-begin creates multiple threads for all the code within the co-begin and prevents the continued execution of code until the co-begin code cell is completely done. So what we can see here is one that each one of these lines, or like aka like how you print in Chapel, is going to be given its own thread. So this is going to be very similar to the begin here, but you don't have to worry about writing the begin syntax. So what's going to happen is that each one of these lines is going to be given to a thread. So one thread is going to say I'm one thread. This is going to be given to a different thread that can say I'm another thread, and then this is going to be given to another one. So same thing as here, we can't predict the order of this, so these print statements can happen in different orders. Another thing to note here is that this other line that says like begin, right line, I am less important and can wait. This line will not be executed until all of these threads are done. So as soon as like every single thread that was given a line here is done, then we can move on to this new line. So now looking at something else, like let's look at sync variables and parallel reduce functions. So sync variables are slightly more complex, where these variables can store value as normal, but they also have 2 states, an empty and full state. A sync variable is set to full when it is given a value, and then is set to empty whenever it is assigned to another sync variable. So for instance, here we have the variable lock, which is attributed to be a sync variable, and it's a Boolean. So here, if we look at what happens, what we're trying to do here is just add whatever iteration we're on. So what happens is that because we're not given a value we don't attribute a value to bool or to lock as soon as we create it, it starts in an empty state, which means that, as we covered before with the for loops, is that we're going to have some set amount of threads that pick up some set amount of iterations. So each one of those threads is going to try to run this code. So they're going to try to attribute true to lock. Only one thread will be able to do this, because the moment that they do it, the state of the lock then becomes full, which means that no other thread can write to it because they have to wait until it's empty. So what's going to happen is that one thread, it's going to write true to lock, which means that it's now set to full. Then it will continue to add the current iteration to sum, and then it'll read the value of lock and write it into unlock to then empty the lock variable. So in simpler terms, whenever you read from it, you are emptying it, and whenever you write to it, you are setting it to full. So as soon as one thread sets unlock to be lock, which means that we're reading lock, it's going to open up lock and now set it to full, or now set it to empty, and then any other thread can then pick up lock by writing the value true to it, which then sets it to full, which means that no other thread can now run the sum plus equals I, which means that here we're trying to combat race conditions with the value of sum by having only one thread at a time write to it and read to it. Now looking at the parallel reduce functions, Chapel provides a built-in reduce function that performs some operation in parallel. You can use the loop as an iterable expression. So here are 2 examples of that. One is very simply just creating a variable sum, which is going to store the reduced array A after we perform the add operation on all of the values within A. Another way that you can do this is by adding an iterable expression, which is what's happening here. So we're going to also perform the operation add, and we're gonna make sure to include the reduce to note that that's what we're doing to this array. That's gonna happen here. Noted here is that because we're doing I and D being some array of let's say 1 to like 4, or 0 to 4. So that means that it's going to have the value 0, 1, 2, 3, and 4. Then what we're going to attribute to that is going to be the array A. So we're going to specifically look at only the first 5 values of A and reduce only those values, which means that we're going to ignore some of the values. Like let's say A is of size 10 and it has like 10 values within it. We're only going to look at the first 5 and ignore the last 5. So our sum is only going to include the sum of the first 5 values. Now, moving on to the future of Chapel. So Chapel was under active development and moving forward rapidly. The language reached a major milestone with version 2.0, released in 2023 and 2024, which provided a stable base of features. The core team at HPE, along with open source contributors, continue to improve Chapel's performance, add features such as improved GPU support, interoperability with C, Fortran, and Python, and they are constantly fixing issues in each release. So now to look at the community, Chapel is open source and the project welcomes contributions. Furthermore, there is a lot of community activity through newsletters, forums, Discord, and many more mediums. Engagement is not slowing down, and the community is invested in the future of Chapel through conversations and contributions. Thank you.